joules per coulomb. Alright, in the second case, we have, well, we didn't do that second part over here. Let's go back and do that. In the second part, Q1 equal to Q2 equal to 2 microcoulomb and Q3 equal to negative 2 microcoulomb. So, what is the total potential? The potential due to Q1 and Q2 will be positive. So, you will add V1 plus V2 and the potential due to Q3 will be negative. So, the result there will be 6,000 plus 4,243 minus 2,683 will be the potential at P due to these three charges. When the charge is negative, the potential it produces will be negative. Alright, let's now go and do the other one. Example 5. A sphere with a radius 60 centimeter has its center at the origin. Equal charges of 3 microcoulomb are placed at 60 degrees intervals along the equator of the sphere. What is the electric field at the origin? What is the electric not the electric field? What is the electric potential at the origin? What is the electric potential at the North Pole? Well, I'm looking for my basketball. You know how handy that comes when we deal with spheres. Now, here is the sphere. What are we supposed to do? And what do we have? We have equal charges of 3 microcoulomb are placed at 60 degrees intervals along the equator. Now look at the equator of the sphere. This is the equator of the sphere. Now if you place charges at 60 degrees interval, how many charges can be placed along the equator? Well, you can place 6 charges because the total degrees for the equator is 360. And at 60 degrees interval, you place charge of 3 microcoulomb. So you got 3 microcoulomb, a 3 microcoulomb, a 3 microcoulomb, like that, 6 of them in equal intervals along the equator. We need to find the electric potential at the origin. The origin is the center of the sphere. We also need to find the electric potential at the North Pole at this point. Alright, well, once you have pictured, visualized the problem, let's draw a diagram. This is the equator of the sphere, and I have 6 charges, each of them 3 microcoulomb, placed at intervals of 60 degrees along the equator. First, I need to find the electric potential at the center. Well, the most important quantity you need to find the electric potential at a point is the distance of the charge from that point. Now, if you notice, each of these charges is at the same distance from the origin. And what is that distance? That distance is the radius of the sphere, which is given to be 60 centimeter. So we know the distances of all the charges. We know all the charges. So what all we need to do is find the potential at the center due to one charge, due to Q1, which will be KQ over R, R equal to 0.6, and then multiply that by 6. Is that right? Because each of them will contribute the same potential at the origin. So Q1 equal to Q2 equal to Q3 equal to Q4 equal to Q5 equal to Q6 equal to 3 microcoulomb. The distances of all 6 charges from the origin are all of them equal to 0.6 meter. The potential due to each of these at the origin therefore is the same. What is the total potential therefore? Each of them will contribute kq over r. Therefore, the total potential at the origin will be 6kq over r. And that will be 6 times k. Q is 3 microcoulomb, r is 0.6. And that is 2.7 times 10 to the 5 volt is the potential at the origin. Well, next we need to find the potential at the North Pole. And again, the first thing we need to figure out is what is the distance of a charge from the North Pole. Now, if you can visualize the distance of a charge from the North Pole, that distance is actually the hypotenuse of a right triangle. And what are the legs of that right triangle? This radius and this radius. You see, if you draw a line from the center to the North Pole, draw a line from the center to the North Pole, that will be a radius. Now that is what I have actually done here. This is a line from the center to the North Pole. That is the radius, that is 0.6. And the distance from the center to a charge is again the radius, that is 0.6. Now the distance of the North Pole from a charge is the hypotenuse of that right triangle. Now what is the length of the hypotenuse? That will be square root of 0.6 squared plus 0.6 squared. I hope you got the picture there. The distance of the North Pole from each of the charges is the same. And that will be this distance, that will be square root of 0.6 squared plus 0.6 squared, that is 0.85 meter. And therefore, all the 6 charges are the same, and all the 6 distances now are the same, and therefore the potential at the North Pole is 6 times kq divided by r, where r is 0.85. So the total potential is 6 times k times q is 3 microcoulomb divided by 0.85. That is 1.9 times 10 to the power 5 volt. All right. We will now look at potential inside and outside a spherical charged shell. Well, we are back with our shell. We talked about it in the last class. Tell me, we have a spherical shell, again my basketball. We have a charged spherical shell. What is the electric field inside the charged spherical shell? You remember the experiment done by Faraday? Yes, the electric field inside a charged shell is 0. Therefore, what is the potential inside the charged shell? Well, let's look at the relationship again. We have the relation between electric field E equal to dV by dr. Therefore, dV equal to E dr, or the potential V equal to integral of E dr. Alright, if you know the meaning of this, now tell me. E is the derivative of V with respect to R. This is R, dV by dr. And E, the electric field inside the charged shell, is 0. Therefore, what can you say about the electric potential inside the charged shell? Well, the derivative of what kind of a quantity will give you 0? If this E has to be 0, then this V has to be a constant because only the derivative of a constant becomes 0. Now in the same way, if you use integration, v equal to integral e dr. E is 0. What is integral of 0? If you integrate 0, what do you get? A constant. So what is the electric potential inside a charged shell? Well, the electric potential inside a charged shell is a constant. In other words, everywhere inside the shell, the potential will remain a constant. Consider a spherical shell of radius r carrying a charge q. In order to find the potential at any point outside the shell, if you want to find the electric potential outside the charged shell, you have to assume that all the charges are concentrated at its center. We talked about that in the last class. Now, potential at a distance r from the center of the shell, therefore, is Vr is kq divided by r. And this is valid only for points outside the shell. Well, thus the potential on the surface of the shell, what is the potential on the surface of the shell? Is kq over r, where r is the radius. So, the potential on the surface of the shell, everywhere on the surface of the shell, the potential will be a constant, and that will be kq divided by r, where r is the radius of the shell. And at any point outside the shell, the potential will be kq over small r, where that small r is greater than the radius. So if you go away from the shell, the potential decreases, right? The potential has a maximum value at a point on the surface. As you go away from it, the potential decreases. Alright, now tell me, we just found out that the potential at any point on the surface is kq divided by r. And we also said earlier that the potential inside the shell is a constant. Now what will be that constant value? It will be the same as the potential on the surface. So the potential at any point on the surface and at any point inside the shell will be kq over r. The potential at any point inside will be a constant, which is the same as the potential on the surface. So the potential on the surface of a charged sphere is kq divided by its radius. Inside the shell, the electric field is 0, and so the potential must be a constant. Since the potential on the surface is kq divided by r, it means the potential at any point inside the shell also must be equal to kq over r. Alright? So, potential at any point inside the shell and at any point on the shell, the potential is uniform, is given by kq over r, and potential at any point outside will be kq divided by small r, where small r is the distance of the point from the center of the shell.